Alright, silly people, here's the situation. Somebody requested this problem specifically out of Goldstein, which is the only reason I'm coming out of hibernation. Um, so I was gonna accept this challenge, and it was quite the challenge to solve it, but I think I've got a solution that I like for it now. So, of course, it starts off with defining a coordinate system that we're going to be working in this situation. So I've drawn the situation described in the textbook, again with some labels for some distances and some angles and some spring constants. So there's that. Keeping in mind, we're keeping the origin of our x and y coordinates up here in between the anchors of the springs, and we're keeping our we're defining the angle phi to be the actual angle that the center rod is making with respect to the horizontal axis as it rotates. That way you can easily set up a Lagrangian for that. But okay, speaking of that, let's set up that kinetic energy, the easier part of the Lagrangian to set up. It's going to have some translational piece, so that's going to be m over 2 x dot squared plus y dot squared. And then it's going to have some rotational piece where it's the moment of inertia divided by 2 times the phi dot squared, the angle of rotation dot squared. And thankfully, the moment of inertia for a one-dimensional rod is just ml squared over 12. So we can skip right to using that. That's m over 2 x dot squared plus y dot squared plus m l squared over 24 phi dot squared. And I'm going to group this together in a much nicer way, I think. Let's pull out m over 2 from everything. Make some big brackets, so that's x dot squared there plus y dot squared there. And then I want to have a just a constant that's squared, so I can use the kinetic energy matrix equation directly. So that's why I'm going to pull out a factor of 3 from that 24 as well, which leaves you L squared phi dot squared over 4. So you can just collect that as L phi dot over 2 all squared in those brackets. Yeah? So now that we've done that, notice here that this guy, and this guy all have units of meters per second, which means we can use this system of things here as our like generalized coordinate system. So I'm saying that the generalized coordinate system is eta 1 is x, eta 2 is y, eta 3 is L phi over 2, and that I'm just going to shorten it to z later on. So I'll even go ahead and rewrite the kinetic energy as m over 2 times x dot squared plus y dot squared plus 1/3 of z dot squared. Right? Now the kinetic energy matrix obeys this equation here that says T equals 1/2 of T ij eta I dot eta j dot. So thankfully there aren't any cross terms, and there's just the terms that are just generalized coordinate squared, generalized coordinate squared, generalized coordinate squared. So we could very simply set up the matrix then to be m, m, and m over 3 for x, y, and z. And then everything else is 0. Like I said, no cross terms in there. And I think now we're going to get to the bulk part of the video, which is actually calculating the potential energy matrix there. So remember the formula for potential energy here is going to be some gravity, which I don't even think we don't really need to include it if we want to get the right motion of this, but we'll include it just for fun. So I'm calling it minus mgy plus y naught. It's a negative sign because I defined my y like axis to be pointing down in this problem, so minus sign. And then it's y naught is some offset because we know that it is going to be, you know, in its equilibrium position, the rod is going to be some distance y naught from the ceiling, right? So that's what y naught is. Plus, and then this is k over 2. The first spring, the spring on the right, I'm going to call S plus, minus the equilibrium length B. So that's the potential from the first spring, whoops, plus k over 2, S minus the spring on the left, minus B squared, where S minus is the, the length of the spring on the left at a given time. So we have to figure out what those S plus and S minus are. As a general sort of formula here that I'm going to write down, it's the distance between their anchor points, and I called their anchor points capital R plus or minus, and it's the distance from that to the, the parts that the springs are attached to the rod. And for that I called that vector little r plus or minus. So it's that distance. Now the anchor points in our coordinate system, we actually know where they are. They're at plus and minus L in the x-axis and 0 on the y-axis. Whereas the spring points on the rod are at more complicated locations. We've got for the spring on the, or for either of them, the x position is x plus the half the length of the rod times cosine of the rotation angle. That's plus or minus. And then for the y position, it's y plus that offset we were talking about, plus or minus half the length of the rod times sine of the rotation angle. Right? So that means we have to find that s plus minus is the difference between those two vectors, and then take the magnitude of that. So it's the square root of r plus minus squared plus r plus minus squared minus 2 big R plus minus dot little r plus minus. And so there's going to be a lot of approximations while I'm expanding this, and I'll make sure to note whenever I'm doing so. But big R squared is just L, capital L squared, L being, the distance between our center of our coordinate system and an anchor point. I don't think I specified that. It's, I'll draw it out. It's this distance here, L, and this distance L. Okay. Just so that we're on the same page. And then this is plus, it's just the dot product of it with itself, so it's x plus or minus L over 2 cosine phi squared plus y naught plus or minus L over 2 sine of phi squared, and then minus the dot product of the two, so that's minus 2 times plus or minus L times x plus or minus L over 2 cosine phi, and it's just that. There's no y component on the anchor points, so the dot product was the most easy part, I think. Okay, so I'm going to fully expand this, and this might end up being a bigger radical. We're going to have L squared plus x squared plus L over 2 squared cosine squared phi plus or minus xl cosine phi plus y squared plus y naught squared plus L over 2 squared sine squared phi, and then all of the y cross terms, so there's plus 2y y naught, and then plus or minus 2yl sine phi plus or minus 2y naught l sine phi, and then actually neither of these two should be there. Yeah, cool. And then that should be all of the cross terms in there. Then we'll hit minus or plus Lx, and then just minus big L, little l cosine phi, and that should be everything. Yeah. Okay. So we want the final form of the potential to be quadratic in the generalized coordinates that we defined, and this radical is going to end up getting squared at some point. And then we're going to want this to be, so in that case we want the result of this to be linear in x, so we can get rid of anything on the order of x squared, y squared, or a cross term if we really need to between y, x, or phi, and then yeah, keep everything else pretty much. So that means that we're going to get rid of this guy here that's on the order of x squared. We're going to get rid of this guy here, the y squared thing, since it's yeah, that's proportional to y squared. And then there's this guy yl sine phi, because because sine phi, whenever you Taylor expand sine, you just get back the angle itself. So that is proportional to two of our generalized coordinates multiplied by each other. So we're going to ignore it as we go. And like I kind of was mentioning, we are going to be using Taylor expansions of cosines and sines to first order. So I'll go ahead and apply those, and also this guy and this guy are going to add up together, so that for L squared over 2, because the sum of cosine squared and sine squared equals 1. So that means with all of those approximations, we've got L squared plus little l squared over 2, little l over 2 squared, I mean, plus or minus just xl plus y naught squared plus 2y y naught plus or minus y naught l phi minus or plus lx minus little l capital L. Right. So that's something. And that's an approximation, so I will put a little approximation there. So now let's go ahead and calculate what B is in terms of all this junk. Remember, B is the equilibrium length of the spring. So we're going to set x equals 0, y equals 0, phi equals 0, and see what we get. We get B is the square root of L squared plus little l over 2 squared plus y naught squared plus 0 plus or minus 0 minus or plus 0 minus little l times big L. So cool. We can take then our, whoops, I haven't done this in a while, I'm a little rusty. s plus or minus then. Take our expression and subtract off the stuff. That's just the equilibrium B. So B itself plus or minus x little l plus 2y y naught plus or minus y naught l phi minus or plus lx. Yeah. So that should be, we've gone a long way already. And I think I missed a factor of 2 way back. So this is a 2 here, and this is a 2 here. That's not even true for that one. The 2 is there. Yeah, I'm comparing with my notes right now, and this is b squared because I don't want to get this wrong if people need help for it. Okay. Yeah. So cool on that. Now we're gonna make another approximation. If we factor out b itself from this, then we get b times the square root of 1 plus or minus, and then I'm just gonna try and combine the stuff dependent on x itself, right? So it's going to be actually 1 minus or plus the stuff dependent on x, and I want to factor out a 2 as well. So minus or plus 2 times L minus L over 2 times x. All of that over b squared minus or plus 2y y naught over b squared plus or minus y naught L phi over b squared. Right, this is looking good. So everything that's not 1 in this square root here is said to be a small quantity. So we're doing small oscillations, remember? And b is already the equilibrium length of the spring, so we can definitely say that all these things are small. So that's why we can make the approximation of this is b times 1, and then we just divide everything else by 2. Minus plus L minus L over 2x over b squared plus y naught over b squared plus or minus y naught L phi over 2b squared. Right? So that's what we got working with. So I'm even going to factor that b through before we do anything else. B minus or plus L minus L over 2 times x over b plus y naught over b plus or minus y naught L phi over 2b. Fantastic. So we can now try and get rid of everything that depends on y naught, big L and little l, and try to put it back into stuff that was given to us in the problem, which, if you remember, was sine theta naught, cosine theta naught, and you know, our generalized coordinates. So I'm zooming back way the hell up here. So what I'm saying is, since this is big L, the distance between the center and our anchor, then it obeys this equation here that this distance here, given by L minus L over 2, is just equal to b sine theta naught. Right, so that's something that we can use to simplify our expression. As well, we know that y naught, which is this distance, y naught is b cosine theta naught. Sir. Sorry, my cat is biting me. Ooh. Okay. We can use those. So we said that L minus L over 2 is just B sine theta naught. Look at that, the B's are going to cancel out. We said that Y naught was B cosine theta naught, plus or minus the Y naught L, Y naught being B cosine theta naught. And then L phi over 2 we said was Z already, so let's just call that Z. And that's over B still. So, like I said, the B's cancel out, and I don't want to be here all day, so I'm going to make some shorthand notation. Sine of theta naught, I'm going to just call S naught from now on. Cosine theta naught, I'm just going to call C naught from now on. And yeah, if we do that, that's going to be B minus or plus X S naught plus Y C naught plus or minus Z C naught, right? That looks very simple after everything, but you know, it took a lot of approximations to get there. Okay, so now we can write out what the potential is, keeping all these in mind. This is still Y plus Y naught. I'm not going to care about converting that into B cosine theta naught, because just Y. And then this is plus K over 2 S plus here, so it's B minus X S naught plus Y C naught plus or minus Z C naught squared, and then minus, or plus actually, K over 2 B plus X S naught plus Y C naught minus Z C naught squared, and this should just be plus here. Okay, so we have to square both of these. Some of the cross terms are going to cancel out, and some are going to add up. So we'll just talk about that as we go. The gravity term remains very, very unimportant. Then we got two factors of just b squared. Oh no, the b's actually cancel out because it's s plus minus b and s minus minus b, so we can get rid of those entirely. So actually it's two factors of x squared s naught squared, two factors of y squared c naught squared, and two factors of z squared c naught squared. Two factors of each. And then we've got that this cross term here will cancel out this cross term. This cross term cancels out this cross term. But this cross term adds to this cross term. So it's plus or minus 4 times x z s naught c naught. Right. That should be good there. And then, yeah, let's factor out a factor of 2, since everything does depend on 2 like that. It's just plus k times all this junk, x squared s naught squared plus y squared c naught squared plus z squared c naught squared minus 2x z s naught c naught. Right. That's what we're going to leave our potential as after lots of work. Let's now calculate the potential matrix. We know that it's just the Jacobian of the potential energy with respect to the generalized coordinates that we came up with. So, right, we got to take 2 derivatives of each on each of these matrix points. So if you take the derivative with respect to x twice, you would get 2k s naught squared if you did y twice, you would get 2k c naught squared. If you did z twice, you would get 2k c naught squared. If you did x and then y, you would just get 0. If you did y and z, you would get 0. The only weird one is if you take x and z either direction, you would just get minus 2 s naught c naught, or minus 2 s naught c naught, right? So that's your potential energy matrix. You can factor out a factor of 2k if you like. So it's 2k times s naught squared 0. Oh, these should have k's on them as well. Yeah. So s naught squared there, minus s naught c naught there, 0, c naught squared is 0, minus s naught c naught, 0, c naught squared. That's the whole matrix. So to find the eigenfrequencies now, we set up the characteristic equation Vij minus omega squared Tij. The determinant of that is 0. For all of our eigenfrequencies, we'll obey that equation. So our kinetic energy matrix was quite easy in compared to this. So we've got 2k s naught squared minus m omega squared, 0 here, minus s naught c naught here with 2k on it, so it's minus 2k s naught c naught. This was 0. This is 2k c naught squared minus m omega squared. Yeah, very simply. And then this is 0. This is going to be minus 2k s naught c naught. This is going to be 0. This is going to be 2k c naught squared minus m omega squared over 3. The determinant of that matrix is equal to 0. And I'll write out it in full and try to proceed cautiously to figure out what the solutions to this equation are. Minus m omega squared over 3 minus 2k s naught c naught squared. There's two factors of that. And then we got this guy. All of that equals 0. I direct your attention to the fact that both of these terms here have this guy attached to it, the 2k c naught squared minus omega squared term. So let's group it like this then. 2k c naught squared minus m omega squared, all of that times 2k s naught squared minus m omega squared times 2k c naught squared minus m omega squared over 3 minus negative 2k s naught c naught squared, like that, equals 0, right? And then work with that. So this is the same constant out here times, what do we got? We've got 4k squared s naught squared c naught squared plus, no, that's minus, minus 2k m omega squared s naught squared over 3 minus 2k m omega squared c naught squared plus m squared omega fourth over 3 plus, or no, this is minus 2, minus 4k squared s naught squared c naught squared. This term cancels this term out, actually, so that's cool. Everything that's left is at least proportional to m omega squared, so we can factor that out of everything. So we can call that m omega squared 2k c naught squared minus m omega squared. And what's left in these brackets is minus 2k m omega squared s naught squared over 3 but we actually factored out the m omega squared, so it's just s naught squared over 3. Yep, and then this is minus minus 2k c naught squared plus m squared, no, just m omega squared over 3 is equal to 0. And what I did to do this is I factored out an extra 1/3 from the last parentheses there to, make this a little bit nicer to read. So it's m omega squared 2k c naught squared minus m omega squared minus 2k s naught squared minus 6k c naught squared plus m omega squared is 0. So the way that I have sort of set it up here, it gets even better because sine squared of theta plus cosine squared of theta is 1. So we can simplify the third parentheses even more to be just minus 2k minus 4k cosine squared theta plus m omega squared 0. I swear this is going somewhere. But okay, this is how we look for our 3 solutions for omega now. The first one, the trivial one, we've got this omega that's completely on the outside, not connected to anything. So we've got a eigenfrequency of 0. Easy peasy. The next one in the line is m1 omega squared equals 2k c naught squared, or in other words, that frequency is the square root of 2k over m times the cosine of theta 0. That's an eigenfrequency. We also need the last equation in the line, so that says m2 omega squared is equal to 2k plus 4k cosine squared of theta naught. So omega 2 is just going to be root 2k over m times 1 plus 2 times cosine squared theta naught. And that's all under a square root as well. So like this. Okay. So 3 eigenfrequencies. I know that if your classical mechanics professor is merciful, then he will let you be done with the problem at this point. But the question does not ask for the eigenfrequencies. It asks for the normal modes. So we have to keep going. So we have to set up the characteristic equation again in its eigenvector form. I'm saying that we have, for eigenfrequency omega j, the matrix, the linear equation is this: 2k s naught squared minus m omega j squared 0 minus 2k s naught cosine naught 0 2k c naught squared minus m omega j squared 0 minus 2k s naught c naught 0 2k c naught squared minus m omega j squared over 3 times the eigenvector a1j, a2j, a3j, that equals 0. So from this you can write 3 little equations just to break it up. So that's 2k s naught squared minus m omega j squared all times a1j plus 0 minus 2k s naught c naught a3j is equal to 0. And then we've got 0 plus 2k c naught squared minus m omega j squared all times a2j equals 0. And then we've got minus 2k s naught c naught a1j plus 0 plus parentheses 2k c naught squared minus m omega j squared over 3 all times a3j is 0. So 3 equations for which you could solve for your eigenvectors. So let's just go down the line with our eigenfrequencies, figure out what these are. The first one, remember our first eigenfrequency was 0. So we have got just 2k s naught squared a1j minus 2k s naught c naught a3j is 0. And then we've got factors of 2k there that just cancel out, and also a factor of sine theta that just gets canceled out. So it's just s naught a1j equals c naught a3j, or you can also, this is for the first eigenfrequency, so let me put the indices here, 0 and 0 and 0, right? So solving this for a10, got c naught over s naught, a30. So the easiest way to set up this eigenvector is we set a30 to some normalizing factor times sine theta. So sine theta naught. And at that point, a10 will be cosine theta naught, and then the normalization factor is actually 1 if you set it up exactly like that. So the first eigenvector is going to be cosine theta naught, 0 sine theta naught. We can take that to the bank with us. Next one, for our other eigenfrequency, 2k over m cosine theta naught, this guy. So, I mean, this, setting it up again, it's 2k s naught squared minus 2k, this time just cosine squared times a11 minus 2k s naught c naught a31 is equal to 0. That's one equation. Another equation is 2k c naught squared minus 2k c naught squared a21 equals 0. We couldn't have done this with the first one because if we plugged in the eigenvalue for the second equation for the first eigenfrequency, we would have gotten that the second equation was non-trivial. But here the second equation is trivial, since this term exactly cancels out this term, which means a21 is a completely free variable. And since a11 and a31 are also free, just dependent on each other, let's just do a21 equals 1. And then a11 and a31 will be 0. So a1, our second eigenvector, will be 0, 1, 0. Pretty funny little cop-out, but it's useful. 2k over m, and then this was the square root of 1 plus cosine squared theta naught. So this one is, I think, the most complicated one, but it's still going to end up being okay looking. We've got that it's just 2k s naught squared minus 2k minus 4k c naught squared a12 minus 2k s naught c naught a32 is 0. And then I'll also write down the second equation this time. I don't think I did it for the first eigenvalue, but I'll show you that it's not a trivial thing. a22 equals 0. Yeah, this inside the parentheses now does not exactly cancel out to 0. So you just have to make the a22 equal to 0. So let's just write out what this is in a little bit more detail. especially considering that minus 2k is actually just minus 2k times cosine squared theta minus 2k times sine squared theta. This is minus 4k c naught squared still times a12 minus 2k s naught c naught a32 is 0. I did that so that we can cancel this piece with this piece, and then this cosine squared piece adds up with this cosine squared piece, so we get it's minus 6k c naught squared a12 minus 2k s naught c naught a32, and we can quickly solve that for a32. We get that that's just minus 3 c naught over s naught a12. Yeah, 6 over 2 is 3, so we got something simple there. So again, we can just call a12 some normalization constant n times sine theta naught, and then a22 is minus some normalization constant n times 3 cosine theta naught, just following from that equation there. And that's 3, 2, mind you. And then we're going to have to normalize this. This is a non-trivial normalization thing. So n squared times sine squared theta naught plus 9 cosine squared theta naught happens to be equal to 1. So in other words, 1 plus 8 cosine squared theta naught is that. So yeah, let's just call n 1 over the square root of 1 plus 8 cosine squared theta naught and call it a day. So that means that our final eigenvector, a3, is sine theta naught up here, 0 in the middle, minus 3 cosine theta naught down here, and then all times this nasty looking normalization constant. Right. Okay. So that's not the end of the problem, but it's very close, since the principal modes are pretty much the inverse of the eigenvectors times whatever, coordinates we defined in the first place. So 801, the principal mode that corresponds to our first eigenfrequency, is just 1 over cosine times x, so x over cosine theta naught, and then 0 over 0 times y, so just 0, and then L phi over 2 sine theta naught there. The 2 we picked up because, again, we defined our third generalized coordinate to be L phi over 2. So that's just, again, the third element of our first eigenvector divided by, or yeah, inverted and then multiplied by our third generalized coordinate, so L phi over 2. So it's that. What that corresponds to, notice that the y component is 0, which means that principal mode is talking about a universe where there isn't any oscillation in the y direction, or at least not for the center of mass. The center of mass is staying still at the same y position, and it's just going like this, right? The rod is going back and forth. You can trace a circle with the ends of the rod in the motion of it. The second principal mode, this is going to be 0 here, and then just y here, and then just 0 here. That was our simplest one. So I believe that principal mode is, yeah, that's the one that's just the rod is moving up and down without really changing the angle with respect to the horizontal. And then the third principal mode is our more complicated one. So that's going to be x over sine theta naught 0, y, that's not y actually, it's L phi over 2, so it's minus L phi over 6 cosine theta naught. And then it's also times this lovely normalization factor that we keep talking about. So that's another situation where, you're not having any change in like the y position of the center of mass here, but because the the third principal thing was divided by 3 this time, it's corresponding to a situation where like it's not a perfect circle anymore. It's something more janky in its motion. I don't know how quite to describe it, but I know that that's how the math works. So you can take that with you to the bank. All right.